Hi, and welcome to your tutorial on using the law of conservation of energy together with a new form of energy to us, elastic potential energy. So thinking back to grade 11 and law of conservation of energy, recall that we had situations where we had the energy in a system before a change is equal to the total amount of energy after the change. You may have seen this with an M. That is, the total mechanical energy before a change in the system is equal to the total mechanical energy of the system after a change. And then you probably accounted for the energy by taking a look at the gravitational potential energy and the kinetic energy, both before and after a change in the system. So an example, of course, is an apple's hanging from a tree. And before it drops, it has gravitational potential energy, described by mg delta h. Because it's not moving, the apple has no kinetic energy. And the second situation we want to investigate is the moment it impacts. So as the apple falls, it's exchanging or transforming its gravitational potential energy into kinetic energy. At the very bottom, where our h is 0, it won't have any gravitational potential energy, and all that energy will have transformed into kinetic energy. And I'm going to say the second velocity is squared. And so last year in grade 11, you could calculate what the impact velocity would be by rearranging and solving this equation. So that's the conservation of energy. You'll remember that in general, the law of conservation of energy is one of those universal laws that exists in the universe, much like the law of conservation of mass, the law of conservation of angular momentum. There's a few others that are defined by the laws of thermodynamics. We're not sure why it is that we live in a universe that have these conservation laws. We've just discovered through experimentation that they seem to be true. And the law of conservation of energy says that in any isolated system, let's try to get the writing going here. Hello. 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 So we can take a look at this example of Simpson's kind of classic bullying situation here, where we have an exchange of energy, a transfer of energy from gravitational potential into kinetic. And as one of the boys has an increase in delta Eg, he falls down, exchanging that delta Eg for kinetic energy. That energy is transferred through the other two boys into the far boy, where he then receives the kinetic energy, and that kinetic energy, because he's connected to the jungle gym, is exchanged for gravitational potential, and then a sloshing back and forth between gravitational potential energy and kinetic. Okay, so let's extend that now to situations where we are introducing elastic potential energy. So in this case, when we take a look at this, we can now add another form of energy, Eg plus Ek plus our elastic potential energy, which is Ee, has to be equal to the combination of all those mechanical energies after a change in situation. So let's take a look at 3 examples today. This is more of a tutorial. I'll look at 3 questions, 3 examples, and work through those for you so you can get a sense of the flow and the thinking that's required. So here's our first example. Example number 1. All right, so here is a little car. That's a terrible car, but it's a car. And it has a delta H or delta Y. At the bottom is a spring with a little bumper on it. And that car is going to come down the ramp, going to hit the spring. The spring will depress or change its conformation or its shape. and we'll push the car back in some direction or with some magnitude. And let's give ourselves some numbers. The classic question will say things like the K of the spring is 4.9 kilonewtons per meter. A kilonewton, 1,000 newtons. So we'll have to do some conversion with the units here. We'll say the mass of the car is 5.0 kilograms. This is a frictionless surface, so there's no loss to non-conservative forces. And what we're asked to find is, first of all, if the spring experiences a compression, the spring compresses, once the car hits it, of 22 centimeters, what is the height of the initial release point? What is delta DH? Okay, so let's delta H. Let's take a look. Change to a different color here. All right. First of all, whenever you see these energy type situations, you want to remember your master equations, and your master equations related to energy is the work energy theorem. And part of that is delta E is equal to E2 minus E1, whatever that might be. And then, of course, we have conservation of energy. With these two master formulas, we can solve pretty near any energy problem. It's just a question of putting them together in creative ways. Well, let's start with our conservation of energy. So we just start by writing that out. And I'm going to leave the M out, although you could include the M because the elastic potential energy is also a mechanical energy. Before the car is released, what form of energy does the car have? I'm going to start by writing them all out, and we can go through them one by one. This is the thinking that you'll have to do when you encounter these situations. All right. So before it's released, there's no kinetic energy. That's 0. And there's no elastic potential energy either. All the energy is bound up in Eg. And then the car hits the spring and depresses 22 centimeters. And that's the situation that we're interested in. That's the second situation. That's the compression of the spring. We're not really interested at this point in what happens afterwards, how far it goes back up the ramp or anything like that. We really are stopping the model once that spring is compressed. So when it's compressed at 22 centimeters, it's not going to have any more Eg. That will all be transformed into one of the other buckets of energy. And neither will it have Ek, because that spring, that's its max extension or compression in this case. So we're left with all the energy that was in that was in Eg is going to be transformed into the bucket of Ee. Then we unpack these. We use the micro formulas. And we know that we have 1/2 K x squared. And we can just put in our numbers. We'll have to do a couple of unit issues here. Our K is 4.9 kilonewtons per meter, which is going to be equal to 4,000 newtons per meter. 4,000 times 10 to the 3 newtons per meter. And then we have an extension, a compression of 0.22 meters, 22 centimeters. Okay, so we can plug in our numbers. The mass of the car is 5 kilograms. G is 9.81. The delta H is what we're looking to solve. We're going to multiply that by 1/2 4.9 times 10 to the 3 newtons per kilogram. Leave the units out just to simplify our math here. And then we have 0.22 squared. And from there, it's just math to rearrange and solve. So here's the rearrangement. We have delta H is equal to 1/2 4.9 times 10 to the 3 times 0.22 squared. And then we're going to divide that by 5 and also 9.81. Some people like to keep that fraction 1/2, so it looks like that. And after punching some numbers in my calculator, I find out that 2.42 meters. So this distance must have been 2.42 meters. All right, that's the flow. Here's another question that we could possibly ask. Let's change to green to mix it up just a little bit. What else could we possibly know about this situation? Let's see if we can calculate the speed of the car. Calculate the speed of the car when the spring compresses 0.15 meters. So it's not at its maximum compression, it's on its way to its maximum compression, but the car is still moving, it's pushing on the spring, but we're stopping the clock here, not at the maximum compression, but we're going to stop the clock before the maximum compression. And so if we zoom in on that, we're going to see the spring and the car. The car is still moving that way. Now the spring was, before the collision, at equilibrium like this, and the distance now is 0.15 meters that the spring is compressed. It's on its way to its maximum compression. So let's take a look at that. It's a different moment in the whole motion here, and we can model that in just the same way. So E is equal to E prime, and we can write our formulas out. Now you may get to the point where you can do this in your head, this step, but for purposes today, I'm just going to keep writing them out. And these are EK prime. Okay, so when that car comes down the ramp and is on this level plane, it's going to hit the spring and it's going to compress it on its way to maximum compression. It has no more EG. EG's all been spent. Or EG's all been spent. The car is going to have EK initially the car does not have EK. Sorry to confuse you, but it will have EK after, at this moment that we're interested in modeling, and there will be no EE initially when the car is at the top of the ramp. So all the energy that is in the EG bucket will now be transformed into two types of energy, EK prime and EE, elastic potential energy. Let's take a look at what that might look like. So we have mg delta H initially, and then these guys are going to have EK prime, which is 1/2 mv2 squared, second velocity, and that of course is the character that we are after right now. We want the speed plus 1/2 kx squared. You can call that delta x if you choose. Okay, well let's take a look. Mg delta, how much energy did we have to put into the system originally? We had 5 kilograms for the mass of the car. 9.81, and delta H we determined was 2.42. So that's the total amount of energy in this closed system that we have to spend, and we're going to spend it in two spots. Some of it's going to go to the kinetic energy, and some is going to go to the elastic potential energy. 1/2 5, change it up to pink, V 2 squared plus, I'm going to run out of room here. Let's move this over, give ourselves some more room. Move it down here so it's not so confusing. Plus 1/2 K, which we determined was 4.9 times 10 to the 3. And the x squared now is 0.15 squared. Well, the EE number turns out to be 119 joules times 1/2 5 V2 squared. And the number for our EE, when you crunch those numbers, seems out of view 55.1 joules. So 55.1 joules of the original 119 have been spent or have been transformed into EE. The rest of it goes into EK. So 119 minus 55.1. And I'm going to keep rearranging. I'm going to multiply that by 2. Divide by 5, take the square root of that, and that will give us the velocity. Now think about that for a sec. We're going to have a leftover amount of energy that will be kinetic energy. And because kinetic energy is a function of the mass of the car as well as the velocity, we can rearrange and solve this way. And we turns out that our V is, oh, where's my notes here? Oh, 5.1 meters per second. Put a box around your answer. Remember to do that. Notice we're still following the DLESS method by drawing a diagram listing what we know and what we want to find out. All right. Let's get a little fancy now and see if we can ask the question, what's the maximum acceleration of the car after it hits the spring? So pretend you're in the car, you're a stuntman, and we're trying to model and figure out if you can do this stunt and survive the acceleration once you hit the spring. So question C, let's find the max acceleration after we hit the spring. Let's remind ourselves of our values first of all. So let's list up mass is 5.0 kilograms. Our K value, 4.9 times 10 to the 3 newtons per kilogram. We're going to go with the maximum extension here, 0.22 meters. Now because now we're dealing with force, we want to remember our formulas. F net equals ma, and we can also use Hooke's law because we're talking about force and springs, that the force that the car applies to the spring is equal to negative kx. So we're talking about acceleration now. We have to use these force equations. So the F net that the car applies to the spring is going to be equal to the Fx. I think I mislabeled this. That is, the force we apply to the spring is going to be equal to the force that the spring exerts. Remember, this is the force that the spring exerts. Learn how to spell. Back on the car. There's our acceleration value, ma. And that's, we're going to get our acceleration from here. It's going to be equal to negative kx. And from here, of course, it's all just simple math. We can rearrange the formula to calculate what our acceleration is of the car. And the acceleration turns out to be 2.2 times 10 to the 2 meters per second squared. And this acceleration is going to be kind of in the negative direction of the vehicle's motion. The vehicle's going this way. Because this acceleration is positive, the acceleration is going to be headed that way. So we can say east or towards the ramp. Let's look at the thinking that allowed us to do that. We put together F net equals ma, which we can never forget, and how forces and springs work together. And I use the expression of Hooke's law that uses the force that the spring exerts onto the car, pushing backwards. And it's going to be equal and opposite to the force that the car applies to the spring. And there we go. Any questions, let me know. Let's take a look at another example. In this example number 2, we're going to have a child on a pogo stick. I don't know, he's not holding on there, that's not safe. And the mass of the child is 48 kilograms. And at the lowest point of one bounce, so the kid's completely compressed the spring as far as it's going to go, as far as he is able. It has, so at max compression, that spring will store 120 joules of elastic potential energy. And it compresses, its maximum compression, x, is 0.19 meters. So this is our EE. And we're going to assume that the mass of the pogo stick is light enough that we can ignore it. We're not going to complicate adding another mass into here because we're focused really on this energy conservation. And the question is, how high is it going to go? Let's determine the max height of the kid. And this is pretty cool that it all works out this way. That we can predict using pretty simple math the result of some kind of mechanical disturbance with regards to a spring. Now, springs are pretty amazing things as long as they're highly engineered. And so let's take a look at how we might do this. All right, well, let's start with our master formula for conservation of energy, because we know that there's an energy transformation. Whenever you sniff out that there's an energy transformation involved, you want to start with energy conservation. And we want to remember, of course, that we may have to pop in and use that guy. And we also remember that delta E can be calculated by taking the second energy minus the first energy state. Okay, so let's write out the types of energies that we can have at the moment when it's maximally compressed. So he's at the lowest point and he's just about to bounce. So our initial state is going to be Eg plus Ek plus Ee. And then his second point, the second point that we're going to model, after the point at which we want to stop the model where the energy is flowed or transformed, is going to be when he's at his maximum height, when he bounces up and he's at some height here, some delta H. So we suspect he's going to have Eg. We know that at maximum height, he's not going to have any Ek, as that velocity vector churns from pointing upwards to pointing downwards. Just like in projectile motion at maximum height, the velocity will be 0. And then we also expect that the EE will be 0 at the top. So we're looking to take elastic potential energy. Initially, we have all elastic potential energy. That spring is locked and ready to fire. And we want to convert that all that energy into Eg. All right, now we did the math up here, or the math is given to us, so we know we have 120 joules of energy to spend, and we know it's all going to go to mg delta H. And you can probably see how simple this becomes once you've figured out how to set up your conservation of energy situation. The math pops out pretty nicely. There we go. And our delta H then turns out to be 0.26 meters. He'll be sorely disappointed that he only went that high. So that's not too exciting, is it? We should have made something a little bit bigger. We can also calculate, set up a situation where what's the maximum speed that he is going to attain. And the point of maximum speed is the point at which the spring is at its equilibrium position, so the spring is not compressed or it's not extended beyond its equilibrium. When the spring is at equilibrium, then all of the energy, EE, becomes zero, and all the energy goes into the other two, EG and EK. So we could calculate that and find our way through that. But I think instead we're going to move on to situation number 3. So example number 3. Hope you're getting a feeling for this type of problem. Be methodical, write it out, draw a diagram, label things, list what you know, and then try to find that relationship between what you know and what you want to find out. Okay, so here's another situation. This is kind of a classic for you textbook question. So you've got a ramp, 30.0 degrees. You've got a spring, and at the end of the spring is a block. Let's make it 3D to jazz it up just a little bit. Ooh, that looks nice. Look at that block, 3-dimensional. And the situation here is that the block is held against a spring, and the block compresses the spring, and then the block is released. And the surface along which the block is traveling is frictionless. And we can analyze this situation in a number of ways. We can calculate how high that block will go up the ramp. Remember that when we're dealing with EG, we're dealing with delta H as a vertical height only. So if the block comes up to this point, we're interested in this delta H, not necessarily the distance up the ramp, unless the question is asking for how far up the ramp does it travel. I just deleted that. I didn't mean to do that. Let's put it back. There we go. So the first question that we'll take a look at is how much elastic potential energy is stored in the spring when it's compressed. So we got to know some numbers here, and here the question is going to give us some of those numbers. So let's say the spring has a K value of 250 newtons per meter. Probably have to know the mass of the block. Let's give it a small mass of 2 kilograms. And when this block is locked and loaded, it's compressed the spring, it's held. The X from equilibrium is 0.22 meters. So it's like a gun, it's locked, it's loaded, it's ready to shoot. And we're interested in A, what is the EE? How much energy is stored up in that block? So our master formulas, you should just write them out every time. That way they're in front of your face when you want to use them. And EE, you should use your formula sheet for, is 1/2 kx squared. So we plug in these numbers, 1/2, our K value, 250 Newton meters, and the X is 0.22. Don't forget to square that. Lots of people forget to square. We find out that at this compression, this spring is storing 6 joules of energy. We should have 2 significant digits here, so we're going to leave that at 6.0. All right, well, what can we do with this then? And we can calculate the speed of the block as it travels along the horizontal surface. We can talk about how far up the ramp the block will travel before it comes to a stop. Let's do that. How far up the ramp will the block travel until it comes to rest? Now this block is not hard connected to the spring. It's going to shoot out like a projectile. Okay, so let's take a look. What are we trying to find here? Well, how far up the ramp? You'll see this ambiguity in a lot of your textbook questions. How far up the ramp? We could be talking about this distance, but we know when we use gravitational potential energy, we're only going to be dealing with this. So knowing the 30 degrees is there, we may have to do some trig to find this delta D there. Okay. Well, let's figure it out. We've got master equation E equals E prime. And we'll write down all the guys that we know, all the players in the game. Plus EK prime plus EE prime. All right, well, let's analyze the situation. This is the physics part of it. When the spring is initially compressed, there is no EG, there's no EK, all we have is EE. We want to stop the model at the point when the velocity is 0 up the ramp, where all the elastic potential energy is being dumped into the bucket of EG, and of course there's no EE. But remember, we're dealing with EG, we're only dealing with the vertical height, so then we're going to have to do some trig to figure out that distance up the ramp. So let's plug in our numbers then. We have 1/2 kx squared is equal to mg delta h. 1/2, what was our k value? Anybody? 250 Newton meters, and the original compression was that. And the mass of this block, we said was 2. Sorry for moving the screen around on you. 9.81. And we want to find the delta H. Rearrange that formula. We find that the delta H is 0.308 meters. Not very exciting. We don't want the delta H though. We want this distance right here. So let's redraw this diagram then. We know that delta H is 0.308. We know that we have a 30-degree angle. And how are we going to find the length of the hypotenuse? That's right, folks. I see that hand back there. We're going to use the sine of theta is equal to the opposite side divided by the hypotenuse. Nice. So we can just plug in our numbers. I'm going to rearrange this as well at the same time. Hope I don't confuse you. And then we find that the length of the hypotenuse, or our distance, is 0.62 meters. There you go. Lots of ways the textbook is going to try to trick you, but always start with the same protocol. That is, draw a diagram, list what you know, write down those master formulas, and figure out from there at which point in the model is certain types of energy 0 and when are they not 0. And once you have gotten to this stage, it's just plug and play. Well, I hope that helps. Good luck. We'll read after the lesson for your practice questions, and we'll talk to you later.